Okay, so we're going to talk about Bayes' formula. And Bayes' formula states that the conditional probability of an event based on the occurrence of another event is equal to the likelihood of the second event given the first event multiplied by the probability of the first event. So what we're going to do is find the probability of an earlier event conditioned on the occurrence of the later event. And it calculates the conditional probability of an event based on the specific related known probabilities. It allows you to update the predicted probabilities of an event by incorporating new information, and often employed in finance in calculating or updating risk elevation. And it's a useful element in the implementation of machine learning. So this is what the formula looks like. We have P of U sub 1 given that E occurred. So that's the probability of U sub 1 given that E occurred equals the product of the branch probabilities leading to E through U sub 1 divided by the sum of all the branch products leading to E. So what does that mean? Well, that means we've got the probability of U sub 1 intersected with E divided by the probability of all of the intersections that will get you to E. So you might have 1, you might have 2, you might have 3, 4, 5 intersections. So basically, like if we look at this problem here in example 1, if here we're looking at the probability of M intersected with A. So this is the M intersected with A means it follows through M and then it follows through A. Now, in the second one, we're looking at the probability of A. That means we've got the probability of M through A and N going to A. So this is where we're going to be looking at the sum of all the branches, and we've got the branches that are leading to what we're looking for. All right, so that kind of gives you an overview. Let's actually go look at a problem. So if I'm finding the probability of M intersected with A, that's going to be equal to the probability of M times the probability of A given that M occurred. So we're only looking at this first one. We're not going to be looking at this one down here because we're only looking at M and not all of A. So using our chart right there, for example 1, this will be the probability of M intersected with A equals the probability of M times the probability of A given that M occurred. So for our numbers, the probability of M is 0.1 times the probability of A given that M occurred, so up here, which is 0.2, and this will get a 0.02. All right, let's go look at our next example. So our next example is example 2. And on example 2, we're looking for the probability of A, which will be equal to the probability of M intersected with A plus the probability of N intersected with A. So I'm kind of writing what's on the problem here. All right, so what does that mean? Well, for each of these, we have the M intersected with A, so that was this part here. So we're going to rewrite this a little bit. So this will be the probability of M times the probability of A given that M occurred plus the probability of N times the probability of A given that N occurred. All right, so now we're going to look at our chart, and the probability of M is 0.7, and the probability of A given that M occurred will be the probability of A given that M occurred is 0.9 plus the probability of N is 0.3 times the probability of A, given that N occurred, is 0.8. All right, so this becomes 0.63 plus 0.24, which will get us 0.87. And that's our final answer. So you're just looking at the tree diagram and figuring out the path that you need to take. All right, example 3. So for example 3, we are finding the probability by referring to the tree diagram. So we're finding the probability of M, given that B occurred, will be equal to the probability of M intersected with B over the probability of M intersected with B plus the probability of N intersected with B. So now we're doing the probability over the total probabilities. So we'll have our top part, we're moving those intersections into the two parts that create that intersection on each of those. So let me write that out. So the probability of M, given that B occurred, will be the probability of the intersection between M and B over the probability of M intersected with B plus the probability of N intersected with B. So just like before, those probabilities of the intersections become the multiplication of those two probabilities. I'm going to go ahead and write this below. So the probability of M times the probability of B, given that M occurred, divided by the probability of M, probability of B, given that M occurred, plus the probability of N times the probability of B, given that N occurred. All right, so on our graph, it's over here on, flip over the page. So the probability of M is going to be 0.8, and then B, given that M occurred, is 0.6. So this will be equal to 0.8 times 0.6 divided by 0.8 times 0.6, that's the same thing on the top and the bottom, plus the probability of N, 0.2, and the probability of B, given that N occurred, 0.4. So these two parts here are always going to kind of be the same, because you've got that probability of the intersection over that intersection plus the other intersections that occur. All right, so if we simplify the numbers on the top, when we multiply that, we get 0.48 divided by 0.48 plus 0.2 times 0.4 will get us 0.8. Yep, 0.08. Let me make sure we have all of our zeros. Want to make sure that we don't make any mistakes with our zeros there. All right, so then when we add this together, we get 0.48, and 0.48 plus 0.08 gets us 0.56. And then when we do the division, we get 0.86. So we actually get 0.857, We'll round it to 0.86. All right, example 4. So find the probability by referring to the tree diagram and using Bayes' formula. So here we're going to do the probability of W given that C occurred. So the probability of W given that C occurred. So we've got these two values here. And then next we'll do W, given that C complement, basically is what that means. That little apostrophe is the complement occurred. All right, so let's switch pages. So if the probability of W given C, we're looking at the product of all the branches, possibilities leading to C through W. So this will be the probability of W. Whoops. Let's do the intersections first, because I think that kind of helps us see the whole thing in the process. So we'll do the intersection of C. That should be intersections. White out. So probability of W intersected with C divided by the probability of W intersected with C plus the probability of U intersected with C and the probability of V intersected with C. So we're looking at all of the C's this time instead of last time we were doing like the B's. This time we're doing the C's. So we've got the probability of the intersection of V and C and U and C. So the probability of U intersected with C and the probability of V intersected with C. The order doesn't matter on how you put this. So W intersected with C will be the probability of W times the probability of C, given that W occurred, over the probability of W, probability of C, given that W occurred, plus the probability of U times the probability of C, given that U occurred, plus the probability of V times the probability of V, given that probability of C, given that V occurred. Lots of letters here. All right. So number-wise, the probability of W is 0.7, and the probability of C, given that W occurred, is 0.2. So we'll have 0.7 times 0.2 divided by, again, that 0.7 times 0.2, and the probability of U is 0.1, and then U C, given that U occurred, is 0.4. And then V would be 0.2 and then 0.3. So 0.7 times 0.2 will get you 0.14 divided by, same number, 0.14. 0.1 times 0.4 will get us 0.04. And then 0.2 times 0.3 will get us 0.06. Oops. Sorry, we're kind of off the writing screen there. All right, so that gets us 0.14 divided by, we've got to add these numbers together, and that gets us 0.24, and that will round to be 0.583. So lots of steps here, but if we do the same steps all the time, you'll get to where you can do that. And you won't have to write all these out. You'll start to see that you're going to know that you're going to take the same route on the bottom. So same route, we're going to the C's, going to C, going to C on the bottom, and the top is just the one where we go from W to C. you'll start to see that, and so you won't have to write all of those steps out. You'll still have to write all of the number parts. I would expect to see all of that when we get to our exam. All right, so this was part A. Now we're going to look at part B. And part B has us doing the probability of W given that C complement occurred. So this will be equal to the probability of W intersected with C complement over the probability of W intersected with C complement plus the probability of U intersected with C complement plus the probability of V intersected with C complement. So this will be the probability of W times the probability of C complement given that W occurred over the probability of W times the probability of C complement given that W occurred plus the probability of U times the probability of C complement given that U occurred plus the probability of V times the probability of C complement given that V occurred. All right, so our numbers, our probability of W given that C complement occurred will be 0.7 and 0.8. And then on the bottom, we'll have 0.7 times 0.8 because it's the same values. And then our probability of U, we're at U, will be 0.1 and C complement will be 0.6. And then for V, we have 0.2 and then C complement will be 0.7. All right, so 0.7 times 0.8 will get us 0.56 divided by 0.56. 0.1 times 0.6 will get us 0.06. And 0.2 and 0.7 being multiplied will get us 0.14. So this will get us 0.56 divided by 0.76, and that will get us 0.737 when we divide them. So again, you won't have to do all of these. You're going to be able to figure this out the more that you practice. All right, example 5. We have a manufacturer that obtains clock radios from 3 different subcontractors. 10% from A, 20% from B, and 70% from C. The defective rates for these 3 subcontractors are 2%, 4%, and 3% respectively. That means that 2% are from A, 4% are from B, and 3% are from C. If a defective clock radio is returned by a customer, what is the probability that it came from subcontractor A, from B, and from C? So again, we're going to be looking at, we're going to create a chart here. We need to create our own tree. We don't have a tree diagram this time. So this will be example 5. And we're going to create the tree diagram. So we will start, and we have 3 places that are making the clock radios. We have A, we have B, and we have C. And then we'll have 2 parts that come off of each of these. We'll have defective, and the D complement, which is not defective, defective, not defective, defective, and not defective. So for part A, our problem said that 10% come from A. We have to put these all in decimals. So 10% would be 0.1. 20% come from B, so 0.2, and 70% come from C. Now, defective-wise, the defective rates are 2%, so 0.02 for A, 4% for B, so 0.04, and for C, we have 0.03 because they're 3%. Now, we've got to find the defective or not defective part. So what we have to do is do some subtraction. So 1, because all of our probabilities add to be 1, 1 minus 0.02. So those two parts there have to add to 1, just like these three parts have to add to 1. That'll get us 0.98. So 0.98. And then this one will be 1 minus 0.04, which will get us 0.96. And this one will be 1 minus 0.03, which will get us 0.97. Okay, so that's creating our chart. And let me just make a note here that D equals defective, and D complement equals not defective. So not defective and defective. Now, we want to know what is the probability that it came, if a defective one, what's the probability that came from the subcontractor of A? So we are looking for the probability of A given that G occurred. All right, so the probability of A given that D occurred. So I'm not going to write all of it out. I'm going to show you how you can do this without writing every step. So the probability of A given that D occurred will be A given that D occurred. So 0.1 times D occurred is 0.02. So that will get us down here, will be 0.1 times 0.02. Plus, we're going to follow all the D's. So 0.2 times 0.04 plus 0.7 times 0.03. So I didn't write all of the intersections and all of that because now we're starting to understand. I'm going to follow this one for this, and then I have to put it over this one, and this one. All right, so 0.1 times 0.02 will get us 0.002 on the top. That'll also get us 0.02 on the bottom. 0.2 times 0.04. Let me make sure. I always like to double check and make sure we're good. All right. So that'll get us 0.008, and 0.7 times 0.03 will get us 0.021. All right, so now we have 0.002, and when I add up the denominator, we get 0.031, and that will become 0.065. All right, now we can do the same steps and understand that when this was for A, now when we do B and C, we're still going to have all of the same denominators because we'll go from B to D And then on the bottom, it'll be B to D, A to D, and C to D. So this same denominator will occur. So we don't have to find the denominator again. So when we go to, this time it'll be the probability of B given that D occurred. We will have the top of B given that D, so 0.2 times 0.04, and then all the same of those will happen, so we know it's going to become 0.031 on our denominator, because you'll have the B to D, which is right here, and the the A to D, and the C to D. So you don't have to redo your whole denominator. So on the top, you get 0.008 divided by 0.031. We'll get a 0.258. And then on our probability of C, given that D occurred, we will have the C part, which is 0.7 times 0.03 divided by our 0.031. So that'll get us 0.021 divided by 0.031, and we'll get 0.677. So that's the nice part. If you have to find all three, once you find that denominator, it'll just be the same and you'll be good. All right, next question. We are looking at a computer store sells 3 types of microcomputers, brand A, B, and C. Of the computers they sell, 55% are brand A, 20% are brand B, and 25% are brand C. They have found that 20% of the brand A computers, 10% of the brand B, and 10% of the brand C computers are returned for service during the warranty period. What is the probability that it is a brand A, brand B, or brand C computer? So we're kind of doing the same thing. So we're going to draw another tree diagram. So this will be example 6. And so we're going to start. And we've got 1, 2, 3. And we still have company A, company B, and company C. And we have returned, not returned, returned, not returned, returned, and not returned. All right, so let's put in our values. So brand A has 55%, so 0.55. Brand B has 20%, so 0.2. And brand C is 25%, so 0.25. Returned is 20% for brand A, and for brand B it is 10%, so 0.1, and it's 10% also for C. Now we need to find our second part, so 1 minus 0.2 will get us 0.8. 1 minus 0.1 is 0.9, and this is going to have the same math, so 0.9. And remember that our R is returned, and this equals not returned. All right. So we're looking at the probability of A given that R occurred. So A let's see, I think we should be at R given that A occurred. Given that, no, yeah. I think that's how it should be. I think we have those written backwards, which is easy enough to do. We know that we're going for the R, but it's given that A occurred. Look. All right. So we'll have 0.55 and 0.2 and then 0.2 with 0.1 on the bottom, and 0.25 and 0.1. I'm thinking that should be R given that A occurred. All right, so we'll have 0.55 times 0.2 over 0.55 times 0.2, and then through the other R, we will have 0.2 times 0.1 plus, we'll have 0.25 times 0.1. All right, so on the top, we will get 0.11. And then on the bottom, we'll have 0.11, 0.02, and 0.025. So this will be 0.11 over 0.155. And this will be equal to 0.71. Now that we have our denominator, when we do the other two, we will, I guess this is the same way. I was like trying to, it's easy to overthink yourself. So A, given that D occurred, and then B, given that D occurred, and C. So that is the correct notation. That's what the other ones had. And I know I pulled it out of the book, but sometimes your logic would be that we're looking for R given that A occurred. But that comes about when we do the other parts of it. All right, so now what we want to do is find the probability of B given R. So B given that R was 0.2 times 0.1, because that's our 0.2 given 0.1 following our B, over our denominator of 0.155. So on the top we'll have 0.025 divided by 0.155. And that'll get us 0.161. And then our final one, oops, sorry. Sorry. I looked at the wrong problem there. So this will be 0.02 on the top and 0.129. All right, now our last part of probability of C, given that R occurred, will be equal to 0.25 times 0.1 divided by 0.155, so 0.025 divided by 0.155. 0.161 will be our total there. All right, so now let's go on to example 7. So on example 7, a new simple test has been developed to detect a particular type of cancer. The test must be evaluated before it is put into use. A medical researcher selects a random sample of 3,000 adults and finds, by other means, that 3% have this type of cancer. Each of the 3,000 adults is given the test, and it is found that the test indicates cancer in 95% of those who have it and in 2% of those who do not. Based on these results, what is the probability of a randomly chosen person having cancer given that the test indicates cancer, of a person having cancer given that the test does not indicate cancer? All right, so we're going to draw another diagram. This one won't be as long of a diagram. It only has 2 parts. So for example 7, we have our start again. And we are going to have cancer, so C. And let's look at that. So, a medical researcher selects random sample of 3,000 adults and finds, by other means, 3% have this type of cancer, and each of the 3,000 adults is given the test. It is found that the test indicates cancer in 95% who have it and 2% who do not. All right, so up here we'll have 0.03, so 3% have this type of cancer. And then up here we will have that when they're given the test, it's 95%, so 0.95. So this will be the test, this will be not test. Now, the other opportunity is other cancer. So if we're looking at the rest of this, this would be 1 minus 0.03. So let's do this off to the side. 1 minus 0.03 equals 0.97. So 0.97. And then we have the T and the T naught, or T complement. All right, so up here we have, and it's found that the test indicates cancer is 95% of those who have it, and in 2% of those who do not. So this would be 0. So this would be like the T or the C naught. 0.02 and 0.98. And we're getting, I didn't write this out. So we've got 1 minus 0.95 will get us 0.05, and 1 minus 0.02. Oops, I have too many zeros. Sorry about that. 1 minus 0.02 gets us 0.98. So that's how we're finding our values. So this is the cancer. This is no cancer. This is our test, indicates cancer. And our test does not indicate cancer. All right, so we're looking for the probability of cancer given that the test indicates cancer. Because we're looking for what's the probability of a randomly chosen person having cancer given that the test indicates cancer. And then of a person having cancer given that the test did not. So they have cancer given that the test said they do. So cancer would be 0.03. Test says they do. So 0.03, 0.95, and then we have to go the other route of 0.97 times the 0.02, because we're going with the T's on both of those. So this on the top will get us 0.285 divided by our 0.285 plus 0.97 times 0.02 we'll get a 0.0194. So this will get a 0.285 on the top, and on the bottom it's 0.479. When we divide that, we get 0.595. So that is the probability of a random chosen person having cancer, given that the test says they have cancer. So if we change that percentage, that's about 59.5% have cancer when their test says they do. All right, now let's go to the probability of cancer given that the test says they don't have cancer. So this will be the probability of cancer, 0.03, with the where it says that the test says they don't have cancer. Oh, I forgot to write that answer in. 0.05. It says they don't have cancer. So 0.03 times 0.05. So repeat those two numbers. Plus then we'll go 0.97 times 0.98. So 0.03 times 0.05 will get us 0.0015 divided by 0.0015 plus 0.9506 when we get those two multiplied. So 0.015 divided by 0.9521 will get a 0.001575. So if we change that to a percent by moving it 2 decimals, we'll still only have a 0.1575%. So not a high percentage of having cancer when the test says you don't have cancer. All right, number 8, we've got a new lie detector test that's been devised and must be tested before it is put into use. 100 people are selected at random, and each person draws and keeps a card from a box of 100 cards. Half of the cards instruct the person to lie, and the others instruct the person to tell the truth. Of those who lied, 95% failed the new lie detector test. That is, the test indicated lying. Of those who told the truth, 2% failed. What is the probability that a randomly chosen subject will have lied that the subject failed the test, and then that the subject will not have lied given that the subject failed the test? All right, so we're starting another diagram. So we're starting again, and we have lying and the truth. And then we either fail or we pass, and we fail or we pass. So again, it says, of those who lied, 95% failed the new lie detector test. What is the probability that a randomly, and then 2% failed the test? So when there's a 50% chance that you are lying or that you're telling the truth. Because it says half of the cards instruct the person to lie and the other instruct the person to tell the truth. So that's where we're going to get the 50% is half. So 0.5 and 0.5, because half are lying, half are telling the truth. Now, of those that lied, it said that 95% fail the lie detector test. And then of those that told the truth, 2% failed. And again, we have to change those to decimal places. So if we have 95% here, then 1 minus 0.95 will get us 0.05, and 1 minus 0.02 will get us 0.98. All right, so now that we have our lied and our truth and our failed and our pass, if we're looking for the probability of somebody lied and failed, because what is the probability that the randomly chosen subject will have lied that the subject failed the test? So lied given that they failed. So lied is going to be 0.5. Given that they failed would be 0.95 over 0.5 times 0.95. And then we have to add the truth where they failed. All right, so on the top, we could probably fit this up here. On the top, we get, that's not, 0.475 divided by 0.475 plus 0.01, which will get us 0.475 over 0.485. And again, those numbers are coming from multiplying here and multiplying there. And when we finally do the division of the rest, we'll get 0.9794. So the probability that a randomly chosen subject will have lied, given that they failed the test, is going to be 97.94%. So if you lied, you're pretty much going to fail. All right, our next one will be the probability that you told the truth, given that you failed. All right, so truth, given that you failed, is going to be 0.5 times 0.02 over, now it'll have the same denominator, right? Because we're going to have this part and then that part. So it's still going to be the same denominator, so we don't have to work all that out again. So on the top, we'll have 0.01 over 0.485, which will get us 0.0206. All right, so we've got one more of these Bayes problems. In a given county, records show that of the registered voters, 40% are Democrats, 35% are Republicans, 25% are independents. In an election, 60% of the Democrats, 30% of the Republicans, and 80% of the independents voted in favor of a parks and recreation bond proposal. If a registered voter chosen at random is found to have voted in favor of the bond, what is the probability that the voter was a Republican, an independent, or a Democrat? All right, so maybe we're going to go ahead and switch pages again. Just so we don't have to hold on to a page while we're on the video. All right, so we're going to start again. And this time we have 3 possibilities. We have the Democrats, the Republican, and the independent. And then the next part is whether or not they voted in favor of the bond. So they were approving the bond. We're going to go with that instead of ayes because we already have an aye. So we have A, not A, oops, not A. Let's take that off with the white out. I don't want that to be confusing. And then we'll have A and A not. So of the Democrats, they were 40% were Democrats, Republicans were 35%, and the independents were 0.25 or 25%. For the Democrats that approved it, it was 60%. For the Republicans that approved, it was 0.3 or 30%, and the independents were 80%. So now to find our other numbers, we take 1 minus 0.6, and that'll get us 0.4. 1 minus 0.3 will get us 0.7, and 1 minus 0.8 is 0.2. So 0.4, 0.7, 0.2. Now A is in favor, A complement is not in favor. All right, so we are looking on the first part is the probability of R, the Republican, given that they approved. All right, so that'll be 0.5 times 0.3. 0.35 times 0.3. All over our 0.35 times 0.3 plus our 0.4 times 0.6 plus our 0.25 times 0.8. So on the top, that'll get a 0.105 divided by 0.105, and then 0.4 times 0.6 will get a 0.24, plus our 0.25 times 0.8 will get us 0.2. All right, when we add that together, we'll get 0.105 divided by 0.545 equals 0.193. All right, now the next one is we are looking at the probability of an independent given that they approved. Well, the independent is going to be 0.25 times our 0.8 over the same denominator. So when we have these multiple ones, once we get that denominator, it does go a little bit faster. So 0.25 times 0.8 got us 0.2. Divide by 0.545 will get us 0.367. And then our last one will be the probability of a Democrat given that they approved. And our Democrat, given that they approved, is 0.4 times 0.6. So 0.4 times 0.6 over that same denominator will get us on the top 0.24 divided by 0.545 gets us 0.44. And that's how you do the Bayes theorem. It's following your tree diagrams of one part over all the different pathways.